So this is Minsuk Kahng, and he's going to be giving us today's tech talk. Yeah, we're very lucky to have recruited him very recently from Georgia Tech. That's where he got his PhD, and he started last winter, 2020, which was a very interesting start time, as you can imagine. But he got to see us all in person for a bit. But since then, we've seen him a lot through Zoom, and I've been collaborating with him on some interesting projects, right off the bat here. So he does really interesting work at the intersection of machine learning, AI, and human interaction. So I think he might view himself as slanted towards the human interaction side, which is great because with his knowledge of machine learning and then the expertise at OSU, there's lots of room for interesting work, and really, it's pretty important that we make these new tools that everybody's hearing about, all the excitement in machine learning, usable by a wider set of people. And so Minsuk and the other researchers like him are going to be the primary ones driving that. So I'm going to let him take it away now. And so what we'll do is, if you do have questions during his talk that you want clarified, you can either unmute, at a pause and ask, or put it in chat, and I'll be monitoring that and I can ask him. And then at the end, we'll have time to pose some questions to him as well. So with that, why don't you get started, Minsuk?
All right, yeah, thanks, Alan, for your detailed introduction. Hi, everyone. So today I'm going to talk about how we can help people interpret AI or the machine learning. So I want to start with a question which has been a driving force behind my work, which is, how can we make AI more human-centered? So by human-centered, I mean making AI more interpretable and accessible so that people can more easily build and use machine learning models. Then you may have a question, why do we need to make AI human-centered? So it is primarily because AI-powered systems are now affecting every aspect of our daily lives. However, people have a hard time understanding how these machine learning models work. So because these models are often very complex with thousands or even millions of parameters. So because of that, people often use these models as black boxes without understanding of how or why they work. And this cartoon shows how machine learning is often used in practice. So people simply pour their data into the system and hope something nice will come out from the other side. So if the accuracy is good enough, they just use it. But if not, instead of finding out why, they just try again and again until they start looking right. So this approach may work fine for some applications, but can be extremely dangerous for some other applications. For example, you may have heard that a self-driving car from Uber killed a pedestrian in Arizona a few years ago. And if we don't understand how these models worked, we will not be able to fix this problem. And the similar accidents may happen again and again. And so the concept of machine learning interpretation or explainable AI has been around, and people are aware of the importance of that. So I had a chance to work with many practitioners in AI, such as data scientists and engineers at Facebook. But they know the importance, but the problem is they lack the tools and techniques to these challenging problems. So my overarching research goal is to help people open this black box. But more specifically, I aim to build an interface between humans and machine learning. So, and where this interface is scalable and interactive enough to work with this complex and larger scale systems. So we're hoping that with such interfaces, machine learning models that perform well will be understood and trusted. And those that do not can be interpreted and fixed. How can you do that? So my key idea or key tool to tackling this problem is using data visualization as a medium for connecting people with the machine learning models or machine learning systems. Okay, then you may question, so what is data visualization and why data visualization here for this task? So here I put one definition of data or information visualization. So the data visualization can be defined as the use of computer-supported interactive visual representation of abstract data to amplify cognition. So let me give you one example by what I mean by this. Probably some of you may have seen this, but this is one example of classic data visualization. So in this particular one visualizes the stock market using a well-known visualization technique called tree map. So here, each rectangle represents a company, and the area of rectangle represents market capitalization. And the color represents the here the 3 months performance. So green is good, red is bad, down. With this visualization, people can immediately see some patterns. For example, first you can see that overall market is good. There are many greens, many more greens than reds, but not for Tesla. So there's the big red portion here. And also a great thing about this tree map visualization is companies are arranged by sectors. So you can quickly see that tech companies are doing great. But for here, there's some area with many reds rectangles for the semiconductor companies. So we can quickly do that. And some of these findings are not easy to get without this type of visualization. Think of how you'll be able to do this if we only have a sorted textual table. So back to the definition. So now you may have a better understanding of what they mean by amplified cognition to understand data. And the natural next question might be, so why are we using data visualization for machine learning interpretation? And so this is the sentence I found from one of the well-known textbooks written by Dr. Munzer. So it says, visualization is suitable when there's a need to augment human capabilities rather than replace people with computational methods. So this means that we don't need visualization if our task has clear answers that can be fully automated, but it can be effective if not. So if you think of the type of questions we need to answer for understanding machine learning models, it very well aligns with this description. So we need to answer a question like, how does neural network work? Or why did my self-driving car crash? Or is my model biased? So there's no clear answer for this question, and it cannot be fully automated by algorithms. We need to augment human capabilities somehow to answer such questions. And also another reason is machine learning is, basically about finding patterns in data, and data are what practitioners care about or are familiar with when they work with machine learning models. So we're hoping that with visualization, people can easily or more analyze and interactively reason about how machine learning models process data. So that's the motivation for using data visualization for machine learning models. And we've been working on that, but it's a challenge problem. So the reason is, I here put 3 challenges. One is modern deep learning models are very complex, as you may know. So it's much more difficult to visualize the behavior of deep learning models compared to linear models. And another challenge is data sets are very large. So if our task is to visualize how a image classification model works for a single image, it's relatively easy to help people understand how it works, but deep learning models often work with billion scale data sets. So what if we have millions of images? Then it's not trivial to visualize results, even results for these large number of images or instances. And lastly, it's challenging to make some visualization or interfaces easy to use for various users. So there are several different types of users for working with AI, and they have different needs. For example, expert researchers who have a PhD in machine learning are more interested in developing new algorithms, while industry practitioners or data scientists may be more interested in applying existing machine learning models to their data set and to see if it worked great. And so designing tools for each of these type of users bring additional challenges. So researchers in this field, in the field of visualization, visual analytics, and HCI, at the intersection of AI and HCI, people have been developing many tools and techniques to help people understand machine learning models. And I have also been working in this area over the past several years. And among all these today, I'll be talking to you about some of these work. So the rest of the talk is organized into the 3 parts. So first, I'd like to talk about how we can visualize for industry scale deep learning models based on my experience working with people at Facebook. And I'll also be talking about how can we support some end-to-end workflow in the various stages of machine learning pipeline. And also, lastly, I will briefly also talk about how we may use visualization for people who want to learn AI. So first, I'd like to tell you about this paper, this work that was done in collaboration with researchers at Facebook a few years ago. This paper was presented at the IEEE Visualization Conference in 2017, and also published in the IEEE journal. So this is the top conference in visualization. And so this paper, invited to multiple venues, and it's excited that this is one of the most cited papers among the main papers in visualization conference. So how did we start this project? So it was several years ago. Engineers at Facebook wanted to develop a new tool for analyzing their deep learning models. And while they have been using visualization tools for some of their existing machine learning models, such as some distant trees, tree-based models, and linear models, however, at that time, they had started using deep learning models, which are much more complex and harder to visualize, which cannot be done with their existing systems. So there are multiple unique practical challenges in visualizing their deep learning models. For example, at Facebook, models are very deep and wide, data sets are huge, and many different types of models and features exist. So this brings challenges in developing some tools, and we wanted to develop a visual system for their needs for understanding their deep learning models. And what we first did is we wanted to deeply understand their needs. So we conducted participatory design sessions with over 15 researchers, engineers, and data scientists at Facebook. And one of the things we were interested in is how data scientists at Facebook currently analyze their very large data sets. And we found that there are 2 key analytics patterns. One is instance level analysis. The other is subset level analysis. So here, instance level analysis means, so user basically pick one instance or say image and see how models respond to that particular individual instance. So this is particularly useful for debugging because it shows data flow from the input layer to the output layer. But the problem is it does not scale because we have to pick one from millions of instances. And so what we found is engineers at Facebook instead like to use subset level analysis. What I mean by subset level analysis is they see whether a model works well for certain topics or certain groups of users. For example, let's say they are interested in classifying some documents, or then they want to see whether a model works for certain topics of the document. So this is great for huge data sets because it provides high-level summary of the models, and both are useful. Both types of analytics are useful. So we wanted to support both types of analysis in our tool. So what we ended up doing is we created this tool, and one of the key idea is we try to unify analysis both for instance level and subset level analysis. And let me show you here the video demo. So this part is the core part of this relation. So here there's a which we call neuron matrix view. So here each row represents instances and each column represents neurons. So for example, the first row here represents a set of here documents where true class is DESD, one of the 6 classes here. And here so each column is a neuron. So this means that here the neuron number 14, we can see the neuron's average activation strength. So darker means so stronger activation here. So and we have subsets like this. And one great thing about this activity is here on the right side, we also have instances. So here, this is the document classification task. So here, each square represents one document. And what they can do is if they choose one of the instances from here, it will be added to the this matrix view. So now you can see that instance number 94, it highly activates this neuron number 6, but not for 8 and 9. And now they can visually see some patterns, activation patterns among instances, like these 3 look similar, but not for the last one, 167, which was misclassified. Then they can also play with this matrix to see some patterns to, for example, they wanted to see why the instance number 167 is misclassified. And they can basically visually see some patterns between those instances, and then they can keep asking some questions and answer the question about that and succeed patterns. So we wanted to evaluate our system. So what we did is we conducted case studies with engineers at Facebook. So we recruited those who created text classification models. So what we did is each participant used our tool for their data set and gave us feedback. And I'd like to tell you some of the observations we saw from the case studies. One is activists basically helps them for spot checking models with their test cases. So I don't know whether you have heard about test cases, but engineers often curate test cases that they are familiar with and for which they know their associated labels. For example, suppose we have a text snippet, let's take a cab, should be classified as a class for transportation related intent. So we know that. And we wanted to make sure that model works great for them. So activists is great for them because we provide some subset level or instance level analysis. Another thing I like to highlight is because this visualization reveals some patterns, user will able to get some hints about how they can further improve the models. For example, let's see, if some neurons are not activated at all, So that may indicate that we have too many neurons here. So they may think they need to decrease the number of neurons. So they can get some type of hints like that. And I'm very excited that the activist has been deployed on FB Learner. So this is the Facebook's machine learning platform for their internally used by more than like 25% of engineers, all engineering team at that time. And FB Learner is a web-based interface, and activists can be launched within FB Learners without having to write much code here. So they have been using this tool for some of the models for deep learning. So that's the first part of the talk I'd like to give today. So let's see. So tools like Activist is great for, as you see, it's great for people's understanding of a single model and single deep learning model. But the issue is not the issue, but the other challenge is model interpretation is only one part of many different tasks in applied machine learning. So, and building machine learning models often involves several analytic stages. So this is the figure from a paper written by researchers at Google a few years ago. So this shows that only a small fraction of real-world machine learning system is composed of the machine learning algorithms. As you see, the small black box here. But the required surrounding infrastructure is vast and complex. And oftentimes practitioners spend like 80% of time on the pre-processing. Probably you may heard about that. So what we wanted to do is we wanted to support those practitioners who work on various stages of a machine learning workflow so that they can identify some problems in machine learning models, potentially fix them, and also discover some interesting new insights about that. So let me give you a couple of, or a few examples around how we can support it. Let's see here. One important challenge is model selection. Engineers often try out many models, and at some point, they need to make decisions of whether they would replace an existing baseline model with a new one. So often, accuracy is an important metric. So however, making decisions solely based on accuracy may be dangerous. So here you see that accuracy for a new model is slightly higher than baseline model. Then should we use that? This is the only information. We may want some additional information to do that. And because even though a new model is more accurate on average, there may exist some populations who would get worse results if we deploy the new model. So, and it is very important for companies like Facebook to avoid this type of situation, to ensure that their models work for everyone and every slices of the data. So here you see that for some population, new models, if we use new models, they would get, the accuracy will be very lower than the other one. This may be okay for some, depending on applications, but this can be more problematic for some cases. You may have heard that researchers have recognized that results from machine learning models can be unfair. So in this example, a face recognition model produced much worse accuracy for female with darker skin tone than for the overall population. So this can result in serious problem as AI-powered systems now make important decisions across social domains. And this is where visual tools can potentially be very useful for humans. Here, practitioners in answering questions like whether my model is fair, or can I use this model or not? So let's see, for this case, generally all the three models work poorly for people with darker skin tone, female. But there's a difference between the gap between the lowest one and highest one. So in 2019, we developed a tool for data scientists to discover subgroups that produce potentially unfair results. And it was also presented at the IEEE Visualization Conference. Here, the challenge is there exists a very large number of attributes or features in data sets. And this can produce a potentially combinatorially large number of subgroups. And Fairvis recommends some underperforming subgroups in terms of fairness metrics by using clustering, and let users explore them so that they can start exploration with these suggested subgroups without having to explore all possibilities. But this process cannot be fully automated. Once suggested, users can see it and play with it and deep dive into it. So that's the idea. So this cannot be automated. We need some mechanism for a human to interact with. And another big challenge in the supporting machine learning workflow, I want to talk about how we can support failure analysis or debugging. This cartoon probably, this is the one I used in the beginning. So it's almost impossible even for experts to build a high-performing model in their first try. So because machine learning model building is an iterative process that they keep finding some problems and fixing them. But for successful iteration, we need to know why it's not working so that we can take the next action. So think of an AI, let's say you're the developer of the AlphaGo AI agents, which you may have heard of. So suppose my agent loses, then we will have a question like, which move caused that loss? Or can I make it work better next time? So we have been working on this problem with Dr. Alan Fern, as you mentioned, and also Dr. Margaret Burnett and our department. So we have been developing a visual explanation tool that describes the AI's reasoning process, and have also conducted many empirical studies on studying how people find errors in reinforcement learning agents and so forth. But even with visualization models, it's still challenging for users to explain complex AI systems. And what we found is, instead of letting users freely perform analysis in such tool, it would be much more effective if we can provide some structured workflow. So here, for example, instead of directly asking them to find out why it lost, we can first ask what was supposed to happen, and then ask what happened, like what is the issue you see. Then you can ask why happened. Then people can build mental models of the agent, and they try to they can better reason about the AI's reasoning process so that they can find more issues and potentially help engineers who would fix this model. So this is the workflow we developed called RFI, and we have been publishing some papers, and we are also working on this. Okay, so that's for the second part. So if you have any question, you can chime in and ask questions. I can ask clarifying questions if you have any. So let's see, so far we've seen how visualization can help practitioners analyze models with very large data sets. But that's not the only population who would get benefit from visualization. So I like to talk about the next part that focus more on people who want to learn AI. So visualization can potentially help these people too. So as you know, I mean, an increasing number of people now want to learn AI as well. So this chart shows the number of students enrolled in AI courses in top universities rapidly increasing. This is also the case for OSU too, as you said, as Alan said at the beginning. So we also launched the AI program, AI graduate program as well, and a lot of students are applying for it. But deep learning is very difficult for beginners to learn and understand. And so we interviewed some of the instructors who teach deep learning at a university at Georgia Tech, and we found that indeed it's challenging for beginners, especially hard to understand connection between the model structures and mathematical concepts. And instructors also believe that some type of visualization may help. And we also surveyed students, so who had previously learned about convolutional neural networks, the popular, the deep learning model, I believe. And what we found is they struggled about understanding the connection between the mathematical concepts and the structure, and also the mechanisms behind the model, including some backpropagation and also how the operation, like convolution operation, works. So this informed us to design how we can design some educational tools for those people to learn about CNN models. And the CNN explainers is the work we developed for CNN. And we also developed the tool called GANLab. This is the tool for learning. GAN is the acronym for Generative Adversarial Networks, which are well known for generating realistic images. And this tool was developed in collaboration with Google People Plus AI Research Group. And I won't dive much into details for these tools, but one thing I'd like to highlight is how we addressed one important challenge in implementing such tool. So since GANLab is an educational tool, we wanted to make it accessible to as many people as possible. However, if we think of deep learning visualization tools, conventional tools require servers that use significant computing resources like GPU. But non-experts or students who want to learn the tool may not have access to such expensive hardware. So what we did is we addressed this challenge by putting everything, including model training and visualization, into web browsers by using TensorFlow.js, the JavaScript framework deep learning library developed by Google Pair, which I also contributed to. So that means now people can use this tool using only their web browsers without the need for installation or specialized backends. So this approach can potentially significantly broaden people's education access to tools like GANLab. So I was very excited that we open sourced these tools and our release went viral, and many people on the world, have shown interest and visited our website. That is a live system, and you can also try it out by visiting this website. So you just need web browser. It even works with some mobile phones. So yeah, so that's the. So let's see. I have 2 more slides left, so I'd like to summarize my talk here. So the question we wanted to answer is how we can help people interpret complex large-scale systems with visual interfaces. And I talked about that visualization can amplify human cognition to find patterns in data, and leading to discovering some insights about the data and models. And when we design such a tool, it'll be helpful if we can provide some kind of summarization or overview first, so that they can get a big picture first, and then we can let the user drill down into details. So that's one strategy we can do. And we also talked about some type of scalable algorithms will be great for working with large data sets. And also, we need to carefully think about how where and how human would be involved in the process. So though AI is great for many tasks, but there are still many things human can do which AI cannot do when analyzing AI model as well. So it's important to design a tool that we can make use of human intelligence. And I think there still exists much more opportunities in helping people more seamlessly interact with AI. For example, this can be achieved by incorporating humans' knowledge back into the AI system for making AI system work better for us. And I envision the next generation of system for people, not only experts, but also for anyone who wants to use AI. And I believe research on creating scalable, interactive visual system for these people will significantly broaden people's access to AI and also ensure their appropriate use. So yeah, this work was possible by many colleagues and collaborators, both in academia and industry, and also funding agencies. And that's all for my presentation today. And thank you for your attention.
Yeah, thanks a lot. Yeah, so we do have some time for questions. I know Charlie, you had a question in chat. Do you want to ask it yourself?
Yeah, sure. Can you hear me?
Yeah.
Yes.
Yeah. I actually jotted down a few more questions, but I'll take turns. That's fine. The first one was with Activiz. You were showing the the activation of specific neurons, cross-tabulated against instances or subsets. But I was curious how you're selecting which neurons to display in that matrix. Assuming you've got a model with a zillion neurons, how does a model builder even know where to look?
Yeah, that's a great question, Charlie. So looking at individual neurons may not work if we have thousands of neurons. So I mean, at that time, so they have been trying out some models that may have like tens or hundreds of neurons. For that type of model, this type of work on looking at individual neurons may work, but may not work if we have like thousands of neurons. So here I didn't mention that, but this projected view and neuron view is complementary, and they can and sometimes looking at individual neurons may work, but sometimes if you use high-dimensional visualization technique like TSNE or UMAP, which you may have heard of, so that might be more helpful. So yeah, there's a trade-off between using what type of visualization, and that may depend on the type of question also.
Great, thanks.
Yeah, you can fire another question or two, Charlie, if you still have some.
Oh yeah, I've got plenty. By the way, I should have said, this is great. This is really, really neat stuff, and congratulations on some of the success here. On the fairness product, FairViz, you had mentioned a caveat on it, and I didn't quite follow that. I mean, I did wonder, for example, if you're trying to evaluate the fairness of, say, image recognition for, say, I don't know, dark-skinned female, the answer you're going to get depends on what you put in, what your input is, right? So you've got that challenge, but you also mentioned a caveat on it, like it wasn't quite ready or something. Could you expand on that?
Are you talking about the challenges I mentioned, or?
Yeah, maybe. It sounded like it wasn't quite at the end quite ready for unsupervised or something. I wasn't quite sure.
Oh yeah, that part I see. So yeah, so this tool is, we are trying to help people discover some intersectional bias. So if we are interested in a single attribute, like we want to see whether model works great for male versus female, or like other attributes like which country, like people in US country, people from US, from Canada. If a single attribute is straightforward, we can just run group by queries and show the information for that. But we're seeing that it's also, as you saw from this figure on the seminal work on gender shades, there might be some populations who get worse results if we intersect multiple attributes. But here they use the two attributes, but we may potentially have a larger number of attributes, some protected attributes, depending on applications. And we wanted to help people explore these possibilities. So suppose we have like 5 to 10 different protected attributes. And if we intersect between all these 5 attributes and values, we will have the combinatory large number of intersections we need to explore, and we're trying to help with that. So what we did is we tried to cluster some spaces to find some potential intersections that may get worse results, that may get some unfair results, and try to help explore that. So here, like each line represents one intersection. So one intersection may indicate like gender equals something, the country, the origin equals something, and like that. Does that?
Oh, I see. So that's the intersection of multiple groups, and then you'll have a false positive rate or something like that. Yeah. So does that mean that the input into this to even create those groups, you've got to have a bunch of labeled data?
Yes. So input to the data set is basically so it's a tabular data that for each, here in case person, we have a set of attributes and we have a label for that, and we also have the prediction result so that we can compute false positive rate or any sort of accuracy metrics or fairness metrics for subgroups. So we can compute false positive rate for people with these feature values, and we can also compute false positive rate for people with this condition or the predicate. Then, and we wanted to compare them and discover some help people discover subgroups who may have very low false positive rate, and then from there they may have some questions like, okay, for this group we have this false positive rate. What about the similar subgroups with this? Would they still get the false positive rate? Then they may have questioned like, is it problematic for our case? Then yeah, that's the end.
Oh, great, thanks. So one last one real quick. The last tool that you showed, which was the explainable AI debugger, that looked like it was analyzing the path through, I think it was a game. What kind of model was that analyzing? Was that a CNN or something else?
This is the reinforcement learning agent we developed with Dr. Alan Fern. So yeah, I haven't explained this domain and agents much. So we developed a StarCraft 2 using the StarCraft 2 game. So basically, we have you can think of the Go game. So basically, we have our agent and we have enemy, and we developed a reinforcement learning agent to predict what would be the best next action I can take, the friendly AI can take, and the visualization is trying to show what actions AI agents, the reinforcement learning agents considered, and then users can see whether their decision makes sense by looking at what they predicted and what they choose among all the multiple actions they can.
Great. Yeah, thanks for that. That's the end of my questions.
Yeah, since I worked with Minsuk, if you're familiar with things like game tree search, like a chess engine, it's kind of like that, but souped up so it can work for StarCraft. And yeah, the deep nets are used to drive the search, basically. Yeah. Does anybody else have questions? I've got some. Yes.
Can I ask my question?
Yes, sure.
So I guess one issue when we want to make our model explainable, especially, for example, for the subgroup explanation, you need to make it make some generalized pattern based on the model that you have. So it means that So it means that when we want to find the patterns and explain it, so maybe the accuracy of the patterns that we are explaining to the end user is not similar to the accuracy of the machine learning model that we already have. So I wanted to say, is there any metric to help us to make a trade-off between the explainability of the model, the patterns that we are explaining, and also the accuracy of the patterns that we are explaining to the end user.
Yeah. I mean, that's a great question. So that's that's one of the main challenges or the problems people want to solve. I mean, when people try to incorporate interpretability into their system. So not every time, but oftentimes, if we want to achieve the interpretability or making models more interpretable, or let's say if we use the simpler models, accuracy may be slightly low. So there's a trade-off between interpretability and the accuracy. So for that case, but there are some mathematical or the machine learning researchers, they want to optimize some of the metrics. For example, let's say we also talked about fairness. So some people may want to may have a strong restriction that they wanted to optimize for fairness, that they want to make sure that there will be no population at all who would get like worse result than like 20% worse than the other one. So we may add that constraint into the optimization process when we train machine learning models. But some may have less restrictions on that. Then they may change the weight for that variable. So it's basically trade-off, and even though it may be optimized, but the person who would use those to make the final decision of how much they want to optimize it for interpretability or the fairness. So it's not the one that can be optimized. So this balance will likely need to be determined by the person who used first, and the algorithm may help with optimizing, finding the right balance between them. So,
thank you.
Yeah. Right. Does anybody else have a question for Minsuk? Either unmute or put it in chat. So if you do, you can put it in chat now. And I do have one kind of general question for you. This is a little more general than just machine learning and user interfaces. But as we get these more intelligent applications for end users, thinking of things like Alexa, if you can call that intelligent, smart vacuums in your house. The interfaces of these things will start to get more complex or have more options. And I'm just wondering if that will get out of control. For example, when I use Alexa, it can be infuriating sometimes how little Alexa can learn and react to basic things. Like it will ask the same thing over and over. And I guess my question is, like for these things to be usable, those interfaces are going to have to be reasonable for end users. And why is it that they're so horrible in many cases? Like, from gossip that you hear at conferences, what is it about the processes that companies use to develop these interfaces that end up with these horrible interfaces? Like, I don't necessarily think Alexa is horrible, but it could be improved in very simple ways, but it's not. So that's sort of a question. Yeah. What is going wrong in your mind in some of these companies?
So when you say interfaces, is it are you talking about the interface for end users, or is it for
this is for the end users, using the product, and and as much as you want to call it an interface, Alexa, you'll ask it a question and it'll give you an answer, and then you ask it's completely off, you ask it the question again and it gives you the same answer, right? These are very easy things it seems to work out, but they're not worked out. And I'm just wondering, why is it? What are companies doing wrong in their design?
I see. Yeah, that's a interesting question. So, I mean, it's about how we can design AI interfaces for end users and how we design the interaction or feedback between the agent or AI agent and the end user. So I think we need some ways to incorporating human feedback in multiple ways, or we may need to a system that can take rich feedback, not just one type of feedback. So when we design a model for, suppose, like, let's say we are developing a RNN model, it basically takes sentence and outputs another sentence. So that's the only interaction models can take. But we may be able to design some clever ways to take human feedback. For example, for the example you gave, suppose users are not happy with one of the responses. If we can say, an end user can say, okay, I don't like this answer. Please don't tell me again when I ask that question. And if machine can somehow integrate that type of more rich feedback into their system and they can take that into consideration, they may work more intelligently. So, but there might be trade-off between the design of simpler models that can take all sort of feedback and how we need to cleverly design what type of feedback we can take and how we can incorporate that feedback into the actual model training process. Well, that's a challenge.
I'm just continually amazed, not just with these interfaces, these types of interfaces, but all interfaces. It feels like sometimes people don't even use them when they put them out there. That's pet peeve, I guess. So do we have, okay, so we do have another question here. So do you want to unmute and ask it? Or I can ask it. So can you?
Sorry, my mic was turning on. Sorry about that. Oh yeah, can you go over the tool used in the second image?
Second image. Yes, I didn't. Okay, I haven't mentioned that. So this is the tool related to the model selection. So this is the workshop paper we published on the model comparison, which I did with the Facebook engineers. But yeah, I didn't show the interface. Looks
oh,
like,
you don't. Oh, I see. Okay.
Yeah, I think you're correct that I didn't cover that image, but I still put that image there in the final slide.
All right. Well, I think we're pretty much at the time limit. So yeah, thanks Minsuk, and thanks everybody for showing up. And we'll have another Tech Talk in 2 weeks. So hope everybody can come, and we'll see you there.
Yeah. Thanks everyone.